Hello, and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 12 in the series on section 3.4, Transformations of Functions. In this section, we're going to learn how we can produce new graphs from a single parent graph by applying certain kinds of algebraic manipulations. We'll begin with the easiest kind, which is to simply take and add a value or subtract a value from our function. Transformations will begin by giving us a parent function, in this case, f of x equal to x, the so-called identity function. You give me an x in, I'll give you an x back. This is just the line y equals x, of course, and so we could plot that on the graph below. The graph of f of x just looks like a 45-degree diagonal line, with positive 1 for a slope and 0, or the origin, for its y-intercept. Now, if we take a look at g of x, we can see what's happened is we have added 3 to f of x. So our transformation, so to speak, that we applied to f of x is to just add 3 to the outside, or to the function f of x itself. That is to say, g of x could be written f of x plus 3. Now, how would such a function look? Well, basically, every y value on the graph of f of x will be increased by 3 units. So whereas before I went through 0, 0, I'll now go through 0, 3. If I went through 2, 2, now I'm going to go through 2, 5, and so on. And what you can see is this traces out a parallel line, also with slope of 1, that goes through the y-intercept of 3. Now that much was clear just from the form of this line. This g of x line has a slope of 1 and a y-intercept of 3. But we want to see this in terms of how we could have transformed f to become g. And in this case, that just means adding 3. So let's describe what's happened. Well, every single point on f of x was increased by 3 units. We have shifted f of x up by 3 units. As we'll go, I'll remark on the rules that we could extract from each one of these examples. Here, when looking at something like f of x plus c, where let's say c is a positive value, the transformation associated to this would be a vertical translation, also called a vertical shift or an upward shift, by c units. And likewise, still considering c to be some positive value, f of x minus c would do what you think it does. This would also be called a vertical translation, but now we are shifting downward by c units. And this gives us our first transformation rules. If we see some old graph plus some constant or minus some constant on the outside of that function, we're just talking about vertically shifting it, either up or down, while the shape of the graph will stay more or less intact. At the end of the video, I will give a digestion of all the rules sort of taken all at once. Here we have another example, this one involving the parent function f of x is equal to the absolute value of x. Let's graph that function quickly. At this point, you should know enough points on absolute value to graph it quickly by shape. There is the absolute value graph with its characteristic V shape. It might be a good idea to memorize the graphs of the basic parent functions that we are going to look at in this video today. Now, here we can see something has changed a bit from before. We're not saying absolute value of x minus 4 here. We've actually put the minus 4 inside the absolute value, and that actually makes all the difference. Now, what would have normally been the absolute value of 0 isn't going to happen until we get an x equal to positive 4. Let's plug in some values into a table to see how this is going to look. If I plug in positive 4 now, we get 0. And likewise, if we plug in 5, we get 1. Or 3, we'll get 1. And we can already see the characteristic V-shape and how it's been shifted. We see that the V-shape hasn't really been distorted too much, it's just been shifted to the right. And that's perhaps surprising because before, when we added something, it shifted it up, which is to be expected. But now that we've subtracted something inside the function, it's shifted us in the positive direction? That seems strange. But here's a nice way to think about it. Since we're actually doing the transformation first, and then plugging it into the function, minusing 4 from each argument means that I will have to be 4 greater before I get to the same arguments that we would have normally plugged into f of x. This is like in daylight savings time, if you have to do such a thing, where you change your clocks to be an hour back. Even though that makes the clock's number go down, now you have gained an hour of sleep because it will take till later for you to get to the same values of time that the clock now reads. The critical observation here is that we note that the graph has been shifted to the right, and that it's been shifted to the right by 4 units. And this brings up 2 more fundamental transformation rules that we should take note of. Again, for simplicity, let's let c be a positive constant. Then f of x minus c is going to be a horizontal translation, and specifically a rightward shift by c units. And correspondingly, f of x plus c would be a horizontal translation in the leftward direction. Again, if this seems confusing, I encourage you to think about when would we get an argument of f of 0. In the case of x minus c, we wouldn't see f having an argument of 0 until x minus c was equal to 0, which would happen at x equals positive c. That's a rightward shift. And in the same way, if we had composed or put inside of the function x plus c, then we would only see a value at f of 0 when x plus c was itself equal to 0, which would happen at x equals minus c, which indicates that the point 0 has instead been shifted to minus c, a leftward shift. This is very similar to the change in sign that happens when you set a factor equal to 0 to find the 0 of that factor. The following question asks about a transformation of y equals x to the third when we add 7. However, I couldn't help but notice that it seems like the adding 7 is missing from this part. Now, when I looked up the actual homework that this is copied from, it seems that there was a problem involving this red font and transferring this over to the paper version of the notes. So that being said, I believe that this problem should actually read, what is the difference between these two plus 7s? Now the question makes a bit more sense, as there is actually a plus 7 which has been done in both cases. And we can compare this to our previous 2 examples to see that a is associated with a horizontal shift because we are composing the function with plus 7, and b is associated with a vertical shift because we have simply added the plus 7 to each y value that is the output of the function x cubed. Number 4 asks us to examine this function and figure out what the parent function should be and come up with a way to describe it using transformations. Here, they've introduced a third transformation in addition to combining the previous 2. You probably can see that there is a parabola that seems to be present here. We've identified the shape of the parabola even when it's tilted to the side. This one seems to be upside down. Recall that that is the shape associated to x squared. And it's helpful when doing these problems to maybe think about the behavior at a couple of points around the vertex, or this lowest point here, associated with the graph of x squared. That is to say, here we are at 0, 0. Then the graph goes over 1, up 1, and unites that with a curve. Then it goes over 1, up 3. In the same way that on this side, the negatively sloped side, we can go over 1, up 1, and then over 1, up 3. Now, of course, going to the left. Do we see something similar with the blue function? Yes, we do. Here, if I go over 1 and down 1, and the next over 1, down 3, I get to my next points. And likewise on the left-hand side, over 1, down 1, over 1, down 3. So what seems to have changed here? Well, quite simply, 2 things have changed. Number 1, it's no longer pointed up, it's pointed down. And number 2, it's been moved, so that the vertex is no longer at the origin, here at 0, 0, it's over here at 3 minus 1. We'll need to take both of those into account. But in the meanwhile, let's address the new transformation which is going on here. If we want to take and reverse the sign of each y value, if we want to point the parabola downward, we could take and reverse the sign of each y value, going from 0 to 0, going from 1 to -1, going from 4 to -4. Such an operation would flip the parabola upside down, and this would mean negating all of the y values. So we take the rules of the function, x squared, and we simply negate them by putting a negative sign out front. The rule associated with this is that multiplying by -1 on the outside of a function will be associated with a vertical reflection, or a flip over the x-axis as such. Now, how can we combine those two together? Well, it can be done one step at a time. We could consider just flipping the function first, which would look like this, and then translating that flipped function over and down. So let's combine those three transformations to produce this final function. The parent function is x squared. If I were to take x squared and negate it, but also compose it with -3, and then on the outside of everything, subtract -1, then minusing 3 on the inside would have the effect of shifting it over by 3. The minus sign on the outside here would have the effect of flipping it over the x-axis, which could be thought of either at the origin or here, it doesn't really matter. And then downshifting by 1 would be precisely what was going on to bring us from here down to here. So those three parts, negating the outside, minusing by 3 inside the function to shift it right by 3, and minusing by 1 outside the function to shift it down by 1, would bring me from this original parent graph flipped down and over to this new graph here. And that's that. This next function doesn't just have the previous 3 transformations, but includes a new one that is distorting the shape of the original parent function. If we squint and flip our head upside down, we can kind of see the original v of an abs-val function. But we see that this absolute value function has been flattened a great deal. Let's see what could happen in order to make such an effect occur. Here is the graph of the original parent function absolute value of x. Now, what would happen if I multiplied on the outside of the function by 1/2 to say 1/2 absolute value of x? Then every y value would be halved. Now, just drawing some points halfway between the x-axis and the green line, we see that we now, instead of having a slope of 1, have a slope of 1/2. And over here, instead of having a slope of -1, we would produce a slope of -1/2. And this has been the characteristic flattening of our function. Likewise, if we were to multiply on the outside by some function that was larger than 1, shall we say, 2x, so 2 absolute value of x, we would have something which was twice as steep because each y value had been made twice as large, except for 0, of course, which stays right where it is. This brings up another transformation, which we could call vertical scaling. We could think about these in 2 cases. One where c is between 1 and 0. In the case that c is small, it shrinks the y values, and we have what is called vertical scaling by contraction, or flattening, or shrinking. On the other hand, if our c that we are multiplying our y values by is a large one, that is to say, if it is larger than 1, then multiplying by c on the outside is still vertical scaling, but now we would call it dilation, or steepening, or stretching. And we might see how this could be combined with reflection. For example, multiplying by -1 on the outside, we saw flips the entire function over the x-axis, but it generally keeps the shape and angles the same. On the other hand, if I multiplied by a tiny number, like say -1/2, it would shrink the y value's magnitude, and the negative sign would flip it as well. Likewise, if we multiplied by a negative number that was of larger magnitude than 1, let's say -2 times the absolute value of x, then we would be flipping from the negative sign and steepening from the large value. And so we would have a graph that looks steeper and also is flipped. And we could think about these as applying the negative sign and the scaling constant separately. The negative sign to flip it, and the scaling constant to shrink or stretch the y values. With that preamble in mind, let's figure out what's going on here. The first thing I like to do in problems such as this is I like to find a key landmark point on the function. And for the absolute value graph, this to me is the corner of the v, right? Where has that gone? Well, it normally hangs out here at 0, 0, right? And now that point at 0, 0 has moved over here. It's moved over here to minus 1, 1. So let's start to keep track of the transformations that have gone on here. We've gone to the left by 1. We've gone up by 1 as such, from our landmark corner at the origin to this new location of the corner. We can also notice that it's been reflected and that it has been compressed or shrunk by a certain factor. To figure out what factor it's been shrunk by, we should take a look at the original graph. The parent function absolute value of x has a slope of 1 in each on the right-hand side and a slope of minus 1 over here on the left. What is the slope of my new function? Well, we have to go over by 4 units before we go down by 1 unit here. Now, the down by 1 unit tells us that there is reflection that's gone on. But the fact that it's no longer 1 to 1, but 4 to 1, tells us that we have shrunk by a factor of 4. That is to say, we have scaled by 1/4. We have divided all of the y values by 4. This is only a quarter. This is only a half. This is 3/4, and this is finally at 1. By the way, another word for this vertical shrinking that I forgot to mention is compression. We would say this has been compressed or squished by a factor of 4. So what is the parent graph that I would use? I would use abs val of x. And then what am I going to do to absolute value of x to make sure that all of these transformations have gone on? Well, number one, it's experienced this reflection. So there's a minus sign that's going to multiply by this thing. It has experienced vertical shrinking or compression by a factor of 4. That means it will be scaled or multiplied by 1/4. It has been shifted up by 1 unit, and so we must add 1 to the outside. It has been shifted left by 1 unit, which means we must add 1 to the inside of the function. It's a nice idea and fairly straightforward to plot these values on a graphing utility so that we could check them. One could either use Desmos, or in this course, since you're allowed to use a calculator, one could also plot them on the calculator. If we first go to y equals, we can put an absolute value graph in here by going to math, then over to number, and clicking abs. That will allow me to put a absolute value of x in the first position, and we could then also plot our prospective transformed function in the same way, and graph to note that both of these functions look the way that we expect. It's a little bit easier to see what's going on Desmos than it is on this calculator, but we can get to what we need on this calculator by zooming appropriately. If we go over here to this area where there's a lot of detail going on and zoom by zooming in, we can see that this function has all the properties that our graph did on Desmos and that our original graph did in our problem. And this is just a nice way to check your work and make sure that you've included every transformation while using an allowed calculator. As we approach this next one, some of you are probably anticipating what comes next. We are now going to put a negative sign on the inside. This will instead be a flip over the y-axis as opposed to a flip over the x-axis. It is horizontal reflection or reflection in the horizontal direction. Here I've drawn an intermediary to show what that looks like as a single transformation before then going downshifting by 2 to get me my full g of x. Now, this can also be done with a number. Let's take some small positive number, in which case this would be called horizontal stretching. And multiplying by some number greater than 0 would be referred to as horizontal compression. Why did we flip the terminology from what it was for vertical? This kind of vertical scaling was called compression. And this kind of vertical scaling is called stretching. Why the reversal? To see that, let's look at a graph. Let's examine the graph of x squared. And consider what happens if we compose by multiplication with 3 versus just by multiplying with 3 afterwards. Notice that both of them have to do with steepening the graph, although by different amounts. But with regards to the horizontal direction, if we imagined looking at things horizontally, then the purple curve has become compressed relative to the horizontal direction. It's as if x values had been squished. On the other hand, multiplying on the outside by 3, we can see that y values have gotten larger. So our x values on this curve seem to be going down from the blue line, but our y curves on the black line seem to be going up. And likewise, if we were to consider a composition with times a third or a product by times a third, then we can see that both of these are shallower, not as steep. They've been sort of depressed from the blue line, but only in the vertical direction. If we consider what happened, for example, to the x value of 1, well, the x value of 1 here at that y value appears at 3. And so we have seen a stretching in the horizontal direction, but a depressing in the vertical direction, where now I am taking 1/3 of the value of 1 to give me a third right here at x equals 1. So it's about perspective. We call this horizontal compression because the x values have gotten smaller for a given y value. And we call this horizontal stretching because the x values have gotten larger for a given y value. On the other hand, this one we would call vertical stretching because the y values have gotten larger for a given x value. And we would call this one vertical compression because the y values have gotten smaller for a given x value. Let's now practice some of these transformations. Here we have a pretty simple one. The only thing that's happening is that we have added 2 to the original function, and we've added it on the outside, meaning I haven't done it before I squared, I've done it after I squared. That means we're dealing with a vertical transformation, and so we are dealing with a vertical shift of 2 units in the positive. That is to say, shifting the graph by 2 units up. We would graph that by taking some landmark points like the origin, or 1, 1, or -1, 1, and upshifting their y values by 2. Connecting the dots, we get a nice graph of our transformed function g of x. Moving on. For the next function, we have negative square root of x plus 3, and the x plus 3 is underneath the square root. That means we've composed addition with x by 3 and the square root function itself. Then we have taken its negative. Taking the negative, or multiplying by -1 on the outside, is a reflection about the x-axis. In other words, it is a vertical reflection. And likewise, because this is composition by +3, we are doing something in the horizontal. We are shifting, because we're adding, in the horizontal, meaning to the left or right. Now, this is +3, so we are going to go to the left. Make sure you get that straight. This is going to be shifting the graph by 3 units to the left. Now here's what that graph would look like. We could sort of visualize this with an intermediary as well. If I were to go over by 3 units and plot some of my landmarks, now shifting their x values 3 units to the left, we would get the following sideways parabola, and then reflecting by taking all of their y values and making them negative, we would get this final form of the transformation. So this would be my g of x, and if this was a test, I would probably erase my intermediary transformation. Here we have another transformation where all that's present is shifting. The internal composition by +1 means we are going to be shifting the graph by 1 unit to the left, and the external composition with -3 means we are going to be shifting the graph by 3 units down. We could do that by looking at the origin as a landmark point and then going left 1, down 3. And we could even do this with a couple points, or we could notice that the next point on the graph is over 1, up 1, or over 1, up 1, and then graph those points as well. Either way, we need to get this purple graph as our transformed function, g of x. Here we have a few things going on in this transformed function. We have a 1/3 multiplying out front. We have a minus sign on the inside multiplying, inside the square that is, and then on the outside we have a +2. On the outside, +2 means we're shifting the graph 2 units up. On the inside, having a negative sign means we've reflected the graph around the y-axis. It is a horizontal reflection. And the 1/3 on the outside means that we are vertically compressing the graph by a factor of 3. Here I've drawn one intermediary to show that if we take minus x and we square it, we just get x squared. A negative times a negative is a positive. And so as such, nothing really happens there if I go from 1/3 x squared or 1/3 minus x squared. These are the same graph. Now, what will 1/3 look like? Well, this is going to look like taking all of my y values and shrinking them by a factor of 3. So, for example, 1 goes to 1/3, 4 goes to 4/3, 9 goes to 3, which is probably our only clean point to plot this with software, and so on. Now we take these points and upshift them by 2 to produce the full g of x. If this was a test, I would erase my intermediary. As it is, I will leave it for the notes. Let's see what's going on here. We've got a 3 multiplying on the outside. A 3 is indeed a number greater than 1, and so we're going to be vertically stretching the graph by a factor of 3. Likewise, we're dealing with composition by subtraction by 4, and that means that we are going to be taking this graph and horizontally shifting it. If it's a -4, we're going to go in the positive x direction by +4 units. That is to say, we will be shifting the graph 4 units to the right. So let's see what that would look like for g of x. We can actually do either of these first. We'll be fine. We could, for example, just look at what happens when we shift it to the right by 4 units. We would get the following parabola. Then to complete my transformation, I need to multiply each y value by 3. That will take, amongst other things, 0 to 0, but also 1 to 3, and 4 to 12, which is already right off the edge of our map. So we're going to have a little difficulty drawing this realistically. Let's just give it a quick sketch. Something like that gets the point across. This is our g of x. Here we have 4 transformations at play. First off, we can see that there's a minus sign on the outside. That minus is going to pertain to a reflection in the vertical sense, that is to say, over the x-axis. Then they are going to multiply the function by 3. This is again going to be vertical scaling because it takes place on the outside of the function, and since it is greater than 1, we are going to consider that to be vertical stretching. Now on the inside of the function, we have a -5. A -5 on the inside is going to indicate that we are going 5 units to the right. And likewise on the outside, we have a +8, which indicates that we have shifted the graph 8 units up. These are the 4 transformations we wish to apply. We could do them in the order of intermediates to see what's really going on. Consider the negation first. That would take my graph and flip the sign of every y value, giving me the following. We could then stretch the graph vertically by multiplying each y value, including 0, by 3. That would give me these points, which I could connect as such. Now we do our transformations by right shifting by 5. That'll take this point and move it here. That'll take this point and move it here. That'll take this point and move it here. And after that, we're somewhat off the edge of the map. And finally, we could take our points and shift them 8 units up. That would take us from here up by 8 units. Again, here at 6 minus 3, up by 8 units to 6, 5, 9 minus 6, going up to 9, 2, and connecting these dots. And that would be reflecting vertically, scaling vertically by 3, shifting by 5 units to the right, and shifting 8 units up. Again, you could delete your intermediaries, erase them, or what have you. This is just a nice way to show my work. As promised, here is a review of the transformations of functions. I will say these are only the linear transformations of functions. That is to say, we're only adding or multiplying by constants, either on the outside or inside of the function. There are other transformations that could be applied as well, but these are what are called the linear transformations, and it's a good place to get started. For the first 4, we have our translations. If c is positive and I add that to the outside, then I'm shifting up by c units. If I am subtracting it from the outside, I go down by c units. And if we put it on the inside of the function, if we also do the function's rules to the addition of c, then we're actually going left by c units, and if we subtract it, we're actually going right by c units. Keep in mind this is against the sign of the axis, while this is shifting with the sign of the axis. If it's greater than 1 and we multiply on the outside, this will be a vertical stretch. All the y values will go up by a factor of c. If we do that with c's between 0 and 1, so some small value of c, this is vertical compression. All the y values will get smaller. If we do it by -1, this will flip us in the vertical direction over the x-axis. And if we wanted to do something for c negative, we could just combine these rules, either combining vertical compression and reflection if we were between 0 and -1, or vertical stretching and reflection if we were less than -1. If we compose with multiplication by c instead, then if c is larger than 1, this is called horizontal compression. This is because for given y values, the corresponding x value will be arrived at much sooner for a much smaller value of x. And likewise, we have a switch. If we multiply on the inside by a c between 0 and 1, this is horizontal stretching. Notice how that shifts terminology from when we looked at the vertical case, similar to how our sign shifting changed when we looked at the vertical and horizontal case of translation. Oops, that should be a -1 here. If c is equal to -1 and we compose with that on the inside, so if we have like f of -x, this pertains to reflection over the y-axis. That's reflection in the horizontal direction. I encourage you to think about things that happen inside the parentheses or within the function as being horizontal type things, and things that happen outside of the function, be that multiplication or addition or subtraction, as vertical type things, either translation in a vertical way or stretching and compressing in a vertical way or reflecting in a vertical way. It appears that we're not going to get into much discussion in these notes about what happens when we combine horizontal translation with horizontal scaling. And so I would just like to mention one thing before we go. Let's take, for example, 4x plus 2 as an absolute value. Now, the question is, which should I do first? Should I scale first or should I shift first? And the answer to this question can be found by asking, what happened to the landmark value at the origin for the parent function? We can see that the main point of this v is at 0, 0. What happens to that point? When is the new argument, that's the internal part of the function, when is that going to be equal to 0? When is 4x plus 2 equal to 0? And what we will find is that's actually at -2, divide by 4, divide by 4, x is equal to -1/2. Interesting. So we haven't even shifted a full unit. We've only gone here. That's pretty interesting. Let's notice that if this is my -1/2, let's make some tick marks on this graph. That means this is a point on my graph. My origin corner of the v is only gone over by -1/2, not 2 as you might have suspected. And let's plug in some more points to see if we can identify some more about this transformation. If I plug in 0, I get 2. If I plug in 1/2, I get 4. And so we can see this has gone over by 1 unit and up by 4 units. My slope is now 4 times steeper. Likewise, plugging in -1, I get a 2 here. And plugging in -1/2 or -3/2 would still give me 4, as expected. So what are the takeaways here? It would seem that something about the scaling by 4 is actually messing with our translation. Let's identify the transformations. This has undergone horizontal compression by 4, but it has been shifted left by 1/2. How might we have seen this without plugging in a bunch of points? Well, the way that this would have worked is to take absolute value of 4x plus 2 and factor out the 4. I need to write this with the composure of plus something deeply inside of the function. It needs to be right next to the x. If I factor out a 4 from both terms, I get the following. And then it's perhaps more clear that what we have is left scaling by 1/2, followed by horizontal compression by a factor of 4. So I will just say be careful in this case where you have a combination of adding and multiplying by constants inside the function, what we would call a full linear composition, because in this case, you're going to have to be cautious about how much you really shifted that function over. However, if you write it as just parentheses x plus something and you factor out that scaling coefficient, you can see pretty easily how much you'll need to shift by versus how much you are scaling by. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.